We have a really exciting speaker today in our seminar series. The speaker is Dr. Ulas Bagci. He's a tenured associate professor at Northwestern University's Radiology, Electrical, and Computer Engineering and Biomedical Engineering departments, and a courtesy professor at the Center for Research in Computer Vision at the University of Central Florida. He directs the Machine and Hybrid Intelligence Lab at Northwestern. His research focuses on artificial intelligence, machine learning, and their applications in biomedical and clinical imaging. He has authored over 330 peer-reviewed articles and holds several NIH grants as a principal investigator. Previously, he was a staff scientist and a lab co-manager at the NIH Center for Infectious Disease Imaging. He's a steering committee member of the NIH's Artificial Intelligence Resource and as an associate editor for several top-tier medical imaging journals. Today, in his talk, he is going to talk about trustworthy AI for imaging-based diagnosis. In this talk, he will address the failures of deep learning and AI algorithms in medical imaging. He will discuss approaches to increase robustness, including algorithmic robustness, interpretable machine learning, and human-in-the-loop systems. And then he will provide examples from applications in prostate cancer MRIs, pancreas cancer scans, liver cirrhosis imaging, lung cancer, and pulmonary disease CT scans. We are grateful, Ulas, for joining us in this seminar, and we look forward to hearing your exciting talk. Thank you.
Thank you very much. Thank you very much. This is very warm welcome, and I'm really honored to be here. Today, I'm gonna talk about this trustworthiness. It's a very broad topic. However, we define like three major steps, especially in medical applications, that how we can actually elevate AI algorithms in a trustworthy level that patients can trust, doctors can trust, and even the software people like scientists can also trust. So just very brief introduction about our laboratory. You already they gave most information. So we are in the city center of Chicago. Our laboratory is in the radiology department, and we are surrounded by like 13 hospitals, so very critical location for us, especially for AI person who needs data. I'm a part of cancer center, so we have multiple ongoing actually the cancer studies from the liver, the pancreas, the prostate, and many others. We have actually more than 30 people in the lab. Some of them are actually volunteers. So these are actually some of our members. I'm really grateful to them, from clinicians to even high school students. Actually, they are doing really great. I'm gonna give some examples today that all these people were involved in our algorithm development process. So our laboratory's name is actually, it's not only machine intelligence, but also hybrid intelligence. The research agenda we have is in many of our applications. These are high-stake applications. This is critical applications, these high-risk applications. So we believe that one of the key to improve the robustness and trustworthiness is to include the expert in the loop system. So the hybrid intelligence is coming from there. So we try to deliver excellence in clinical AI applications, and we do actually an extra effort to transfer our algorithms into the the clinical use and to see how it is the successful. And we look at the interaction between experts. In our case, mostly this is radiologists, but also clinicians as well, to see how the AI is helping them, and at the same time we try to learn from clinicians to improve the AI algorithms. So we define actually three steps for trustworthiness. One of them is algorithmic robustness. Almost everybody in AI field, like in medical AI field, every day you see applications like the new architectures are coming, new algorithms are coming. Some of them are major, some of them are incremental novelties, try to solve a specific medical imaging problems. And there are also, these algorithms need to be tested against different centers. Generalization is the big problem. and out of distribution samples are important to to consider. These are the topics of actually interest algorithmically we are actually developing. We have, like many other people in this domain, actually we have new algorithms for segmentation, for example, transformer-based, unit-based. We have also such algorithms to solve specific problems, and when we develop these algorithms, we pay attention to how to make them robustness. Like in all our studies, we try to make them like multi-center so that you have enough data heterogeneity. We try to look at actually the race and gender distribution. These are actually the important robustness criteria. For interpretable methods, which is the second choice, for the trustworthiness, actually, there are two interpretability, the concept, which is also a little vague in the field. There is no one definition really for this. People use usually interpretable and explainability in exchangeably. So a model, deep learning model you develop should be, interpreting its results to, the users. So why that decision is taken. So that is the main thing. If it can explain the decision and if this decision is trusted by the user, so we can say that there is at least some trustworthiness level is reached. Another one that the third step is actually we call the expert in the loop system. So in order to increase the trustworthiness of a system, including a clinician or radiologist or even more clinicians in the loop for an AI system is going to increase the trustness, because the human factors has a lot of the benefit in this. So in this today's talk, actually we have a lot of algorithm papers, which I call them mathematical gymnastic. It is not bad thing, but it is like yet another paper similar to the literature. There are interpretable methods like the radiologically explain the radiographically explain a decision, or explain visually what why your algorithm is actually making a decision based on actually these region patterns or saliency maps. These are the things actually we also do that, but today specifically I will work on the in my talk expert in the loop systems, and try to show actually one really nice example that interaction between AI and clinician can be really actually useful. So expert in the loop systems, expert in the loop systems are very important, especially just one thing. Close this, some warning came. Okay. First of all, for ethical considerations, it is important, like, the sensitive domains like healthcare, criminal justice, finance, autonomous driving. It is important to consider some ethical considerations that the human information, the sensitive informations, those things are not really the shared or the kept, the private. So another thing that expert in the loop systems are useful is the complex decision making system. So consider that there is a AI driven actually decision system. Usually how it works, that actually you feed the data, you learn the patterns, but there are so many actually difficult cases, the problems that requires more complex decision mechanism that human intuition can come into the play. Sometimes creativity, for example, is important. And actually another thing is that transparency. So once actually the expert in the loop for an AI system, for a fully automated system, the explainability and the transparency can be actually improved. For complex decision making, actually, I want to also, and related to the domain expertise, give one example. For example, we have a colleague, also good, a good friend of ours. He's a MD. He's not a pathological condition, but his body, the left and right side inside body's organs are shifted by birth. So, for clinician, this is really an easy to understand, the easy symptom, let me say, I'm not the expert to say what the condition is, but for an AI, it's, when you have the radiology images of this person, it's completely shifted and may not really understand if the domain expertise is not inputted there. So sometimes very simple human interaction can make the whole system, easily interpretable and, the working. This is one of the just simple example that the expert in the loop system can be very useful. So how we can include the expert in the loop? So this is, we start with the radiology rooms. So how we can actually include the radiologists in the loop beyond the conventional way of the AI is showing them, some regions which is, potentially pathological things are ongoing or some disease. So, what are the, what are the ways to include them more effectively in the decision system? So, when we look at this typical radiology room, we know that there's a dedicated light source, there's the darkened environment, limited distraction usually, and what they are doing is the visual search and then reporting. So here you see they have a microphone, so they interact with the computer like the PAC system. They look at it with their eyes, they talk, they write. So these are actually some of the things that actually they can interact with the the computer. So while looking at this, all these actual observations, we want to actually utilize all this information to include them in the loop for an AI system generation. And then we start with this with the most important part, which we believe it is the their eye, because what they do is the visual search, right? So how we can actually use their search mechanism in our AI algorithm development. So we will use eye tracking system and AI to achieve this. In order to give just the one clinical examples, okay, they are doing this, but in radiology room, there are so many applications to do. One example I will give here, lung cancer, but we have tried this actually for many different diseases. For lung cancer screening, I want to show the good thing about their screening mechanism, radiologist screening mechanism, and also how AI is doing nowadays, and how these two mind can be integrated together. So the motivation of lung cancer screening is that actually there is a screening paradigm more or less the same all over the world. We know that early stage, if you can capture the lung nodules, you are gonna save people's life, more than 90% survival rate. And we also know that the low dose computed tomography, the CT scans are being used for screening strategies, and they show this seminal article that screening with the CT reduced the mortality from lung cancer. So it is important. During the radiology screening, the requirement is that actually radiologists need to search the CT scan and find these nodules, especially the ones at the early stage, which are small, and then it will really help. But is it that easy to find those nodules? So radiologists are great, but they may really miss the tumors, especially when they are when those tumors are small. So if you look at this CT scan, especially the tiny small tumors, actually it can be missed really easily. There are so many biases when radiologists are actually looking at these tumors. Here, for example, it looks like really the normal tissue. There is actually a very small nodule here. It can be missed, and we know that actually there are so many other biases in radiology rooms. So there is this radiographics journal paper. It's the how and why of misses and misinterpretations. Pretty nice. Around 20 the medical the reasons for medical errors, the radiology errors, are actually interpreted here. Two of them are very interesting for us. Actually, we were thinking that when we start this project, if we can really catch those biases and reduce the human error. One of them is the satisfaction of search error, which is when radiologists, for example, find one tumor, when they search, their vigilance is decreasing after, they are aware that they already find one tumor. So then their attention is actually reduced, and they may miss some of the other tumors or conditions happening in the other part of the body. Another bias is called inattentional bias. So we believe that we can also with AI, we can also help this search bias as well. So this is like the reason is that missing the findings, hiding in the plain sight due to unexpected location or nature. So they are very similar to the normal tissues as well. So this is another one. So there are so many other biases in radiology room. So these two are very important, and I think AI can help to reduce. This is how we actually really started our project for human in the loop, and consider that like AI should help radiologists for this reducing these biases, and at the same time we can learn high-level information from radiologists to integrate into the the AI to increase the trustworthiness. So we know that the 35% of these small lung nodules are typically missed during the screening process. Probably this rate changed in recent years. So human error remains a significant problem to detect abnormalities. Another problem is the overdiagnosis. So for this typical CT scan, actually, if you look at this CT scan, you will see actually one tumor actually is right here. And this is satisfaction of search problem, actually. I can show here that if you notice on the other side of the lung, there is a gorilla is hidden. This study is actually the Dr. Jeremy Wolf's study. It is a perception study. He showed that 20 out of 24 radiologists in this experiment, actually, they didn't report this gorilla because they focus on the nodule. So there is a satisfaction of search actually problem here. And this is very actually famous study showing how important, the human error in the, the radiology room. So deep learning can help, like it is everywhere. So every day, actually, we see how deep learning is solving many medical problems. Almost every day we see, the such news, but they are also not perfect. Like not only trustability, but also their, its performance is not that in the desired level in many applications that they are going into clinics. For example, for lung cancer cases, actually, you can see so many false positive here. These red, the red circles. So for a radiologist, this is easier to actually fix. And we know that for a radiologist, it may be also difficult to catch the, the missing tumor, this small tumor. So both AI and radiologists actually have, the positive and negative sides. And what we are thinking that we should really combine this in the non-conventional way, like not like a stepwise help each other, but to jointly combine their strengths. So the human expert can miss tumor cases, and we know that machine learning can help finding those small cases, small tumors, and we know that machine learning can produce many false positives, which human expert can easily help them. So this is how we started with lung cancer and how to incorporate actually human in the loop for such an AI system, and then move into other organs and screening procedures as well. So based on, all this, the observation, so we decided to actually how to use, especially the expert radiologists' visual pattern, like how they screen very fast and find all these tumors, and they ignore false positive regions. Like we really need, especially that ignoring the false positive regions to embed into the AI. At the same time, if there is a, the small tumor that, or any tumor they are missing or pathology they are missing due to some biases, we should also show to them so that actually they learn from AI and we learn from, AI learn from radiologists. This is a typical eye tracking system nowadays. In the past, there was actually glass-based systems. Nowadays, actually, we put them with eye tracking into the, the beyond behind the screen. And then it doesn't really bother. It is a stereo camera, and we follow actually how the radiologists look at the screen. This is on the right-hand side, you see as, the sample attention map. These are the true attention map, like the biological attention map. It is not the computer attention map. Like in computer domain, AI domain, there is also this terminology called attention, which is usually derived by the algorithm to showing the most correlated regions, most learned patterns. So I have a funding for this. It's called RCI, Radiologist Center AI, and we started with lung cancer screening, but I expanded this for the pancreas, liver, prostate, and actually it is actually working in most of the screening cases. Of course, it's also, there are so many difficulties, which I will tell why. The main motivation here was that the two brains was actually better than one. And one of them is the human. So the high level recognition is better than deep learning still. While deep learning algorithms are really good at local tasks like finding the pixel level calculation and all those things, actually deep learning is better in the superhuman level, while for more high level, more reasoning kind of stuff, radiologists are and the humans are better. So that is the idea how we can actually fill that gap in AI to, improve the, this AI-based actually systems. This was actually our initial experiments. Several years ago, I started at NIH. So the thing is, there were actually many eye tracking studies already in the literature, but none of them were actually in the real radiology room settings. They were all in laboratory settings, 2D, slice by slice, and so many restrictions. So one of my aim was to make this in radiology room settings in 3D, the volumetric settings, and let radiologists to play with the the contrast, and this can go over the the slices, can make zoom, can change whatever they want to change in the screen, and also use their the regular screening procedures. And in different actually condition, in light environment, in dark environment, they should really able to use this. So I wanted to make this really realistic, and I noticed there was no realistic radiology room screening system, which actually I was able to manage to build this, which actually took many years. It was very difficult to consider all the mouse keyboard movement, all this, the manipulation on the screen, opening the images. Radiologists look at different screen, the screens. These were like a really engineering effort to consider the system right in the radiology room. So we call this initial system like the CCAT, like real true collaborative CAT. So it's not like the helping just human, but it is because we at the same time from AI learn from radiologists how they search this pattern. So initially, actually, we started our system with at that time, these glass-based systems were very popular, but it turned into also this Fovio and other devices. It is under the, the screen. We put them, this is our earlier, one of the earlier actually, the eye tracker. Nowadays, we also use, a little bit more advanced model as well. A typical attention map, biological attention map actually is seen on the right-hand side, showing where the radiologists spend more time. There is a very little angular error for this eye tracker. Before we do our experiments and all the screening, for every user, actually we do a calibration. Then actually we continue actually screening based on each person's the calibration. From the mathematical perspective, I will not spend a lot of time here, but I'm happy to discuss later. So many of these studies actually use just these maps as an attention to do some classification or other things. But we want a AI system which already integrate attention mechanism, like biological attention mechanism. So how, we go into the, this eye tracking systems, and then we understand actually radiologists look at certain parts and they move. And we consider that actually these saccades actually. So the eye movement is called saccades, and the node is where they look at actually, the steadily, it's called fixation. So wherever they look, actually we consider this as a node, and when they move into other parts, we consider this as the saccades. And from pixel to pixels, actually there is a line, like there is a track, or you can call scan path. So we consider this like an edge. So mathematically, actually, we saw that this is naturally very close to like how we can model this as a graph. Graph has a node and edges. Nodes are where radiologists look at it. Edges are actually their path, like screening path. So we noticed actually is, so many nodes and so many edges are there when they look at, the images in 3D. So for one region, actually, if they look at one region, there are so many pixels are already nodes, and the edge. Sometimes they also go back to the same location. So they are repeated edges and they are repeated nodes. is too much. And since we want this system to real time or near real time, actually, we really need to minimize these regions to make the computation efficient. What we did actually is very easy. So we did like a non-parametric clustering. For one region, we don't need to look at 1,000 actually nodes. Just one node is actually enough. And we also find these repeated edges mathematically, like computer-wise, and then remove them from the system to make the whole system efficient. The raw data on the left, actually, you see is the blue. This is all the nodes, like the pixels, regions that a radiologist look at during the lung cancer screening for a CT. So we do just a simple clustering. You see this green and the blue and all other parts are like similar regions. So in order to consider that region, you just need one node. You don't need really thousands of nodes to represent one region. And then we remove like those edges as well. So here actually raw data, then we do clustering. With clustering, actually, we just consider the center of the cluster as a representative of that region. And then we also find the repeated edges to minimize this graph, which is the search pattern. So what is called actually sparsified graph. So it is like minimized graph, but it is representative of the search pattern. And then since this is already in the image, so we can use this information as a biological attention to improve the, the detection, segmentation, and also classifications. Excuse me. So this is already embedded into the CT, and then actually what we have done actually in our early work to multitask CNN algorithm. So because there are, the three tasks there, at least one of them is like find the nodule, and then define if it is a nodule or not, and then the segment it, and then we also consider it is malignancy or benign. So these three things can be done in a one, the algorithm. That's why it's called multitask. When the tasks are associated with each other, doing a multitask learning improve each of these task prediction accuracy as well. So the good thing actually here is that actually this is a generic system. So once the CNN is actually replaced by many other algorithms, like now with transformers, for example, or capsules, or nowadays actually diffusion, you can just replace this model. So it's not necessarily just one typical, the deep learning. So this is a strength of our work. After the CNN, we were working on capsule algorithms, capsule neural networks. They were actually pretty strong in terms of interpretation and robustness. So we replaced our algorithm later with CAPS algorithms. And then recently, actually, since transformers are taking the lead now, giving better results and robustness, so we switch into transformers too. So the whole system is not really changed. How we real time actually got all this eye tracking, put them into the deep learning, real time or near real time, and then embed it into the AI to improve the diagnosis. Three components here, like gaze analysis, visual attention, and the machine learning part. So any improvement in any part of this actually is gonna improve the overall the procedure as well. So this was actually published as a really long paper, is in Medical Image Analysis 2019. I want to show a really interesting actually thing here. One of them is like, the different radiologists have different search patterns, right? So here radiologist first, second, and third radiologist. If you can look at the third radiologist, actually, she's looking at actually more regions in the lung, covering almost everywhere. Radiologist first is actually the most expert radiologist with many years of experience. He's doing actually, if you look at the time, it is like 2-minute search. The other one is actually 6-minute search, 5-6-minute search. Is more careful, and by the the experience is actually increasing the search time, and the search also patterns are really changing. So we noticed that actually we can personalize even this, these search patterns can come into the AI. And this can actually learn for each person. Actually, the AI algorithm can learn their, the search pattern and act accordingly. So that is a really actually nice integration that we start working on this. Of course, we really need actually a lot of data for this, a lot of radiologists to generalize this. But initial, the initial results were actually very promising. Here, the more recently, like if you notice here, so we have like three components, and it's more or less like an engineering concatenation. So so once the gaze is collected with the pattern, actually we really need to minimize this, and then as a visual attention, put it into the regions of the CT scan or MRI scan, and then we do the deep learning component. So our idea was actually more recently, like last year, we published in this winter conference Vision is a premier venue, how actually we can do this just as a single step. So the idea was to use the graph to use the node and edges, like the fixation and the saccades of the data. So the idea was actually, let's use a single graph, but neural networks is embedded on this instead of having like three steps. So this is so we choose actually graph neural networks actually in this case, because the reason is we want to actually, we want to have actually a single step so it can be trained end to end. And also this can actually increase the time efficiency. And also we believe that actually in the graph neural networks, the graphs are actually very flexible, so we can add extra information if we want. And we don't need to use every part of the images if not necessary, right? So because radiologists also do not look every part, which is, false positive may arise in those parts. So we combine image embedding, which is the image itself to be with AI, and then eye gaze information, which is coming from the eye tracking, and we put them into the encoder and the classifier with the prediction. So this is the system actually we have. Eye gaze information is actually that is in the similar way of the image. Actually, it was divided into patches, like in the images actually in transformer-based neural networks. Actually, image usually is turned into a patches, and the patches embedded into transformer. We did the same thing. So the patches from the eye gaze informations are come, and if you notice in the middle, like the eye gaze information and the patches from the image itself are actually concatenated together. And then the graph is constructed. You see the graph actually here. It's very flexible application in this case. And then we use these X-ray images in our experiments to see if this is really useful for improving the diagnosis by radiologists for X-ray experiment. I'm gonna skip this. This is just aggregation of how we divide the eye gaze region. So this is the technically what we have used in this graph. Like there are L blocks and pooling and classification head. And for X-ray images, we will look at actually the normal X-rays, pneumonia and CHF, these cardiac problems, and we try to actually do that with AI, with eye tracking and without eye tracking, and see if there is a diagnostic improvement in the system or not. This GNN is the one actually we proposed to use, compared with transformer, ResNet, and some other benchmarking techniques, already getting like 83% accuracy for this, the X-ray images. GNN actually has some graph neural networks has some actually flexible properties, they are not that data hungry as like transformers, and they are also having flexibility for learning different types of information in a node. So the feature vector for each node of the graph neural network doesn't need to be fixed. So it can be different, the texture, different features can be embedded there. So when we look at the classification results on the chest X-ray data set, we see that actually we got pretty good results, like the 5%, 6% improvement over the other gaze-based, the systems. And when we do the ablation, like with and without eye gaze, we see that 3% accuracy when we use eye gaze information. So I will show now picture-wise, what does it mean? So these are the AUC curves actually showing that actually really good, the results we got. And this is the inference, so one of the things is that this still needs to be very fast, right? So the conventional attention consistency architecture is, they have 0.29 seconds. Is pretty close to, the inference that we have. Gaze GNN is very close, as you can see. It's like nearly real time. While if you use just a classical way of two-stream architecture with gaze, it is like taking some time, like 9 seconds. So this is the, it is very fast, and accuracy wise it is even better. Now the picture wise, what does it mean? So the second column, you see this gaze map, which is biological attention for an X-ray images. This red means actually this incorrect model prediction. AI is making an incorrect prediction, and the green is the correct prediction for different cases like normal pneumonia. Two of them are actually pneumonia. So GradChem is actually the model. It is like saliency map coming from AI. As you can see, the third column is all actually showing not really relevant regions with the the decision. But when we integrate this eye gaze information, this second column, into the first column, which is the image, when we combine together with the human, they are looking at the correct places, then put it into classifier, then all these incorrect model prediction turn into correct prediction. So we improve the model predictions actually, so the further. That's why this 3% accuracy improvement is coming from. It's all from the human better search patterns actually. So I want to show, this is recently what we are using. This is a little bit better eye tracker. And on the left-hand side, you see these green and red regions, which means that actually when radiologists look at the screen and they do this 3D screening, we actually cover all their scan path, like the search mechanism, and then we actually calculate where they look at it, which is green, where they covered it, and where they didn't look at it, which is red. Because one of the things is that if you don't look at it, you may not see it, right? So there is this famous perception paper. So recently what we have done is that actually for the regions that radiologists are not looking, these red regions, we calculate AI again there, only those regions, to see if they are missing anything. So in one of the cases, like we see this red region, they didn't look at it, and there was a small, the lung tumor. So it is like a secondary time, actually we train, and then we find it, and the sensitivity of, such cases like 91%. It's like the backup, the training backup actually decision, and then radiologists can see at the end of their screening where they look at it, where they didn't look at it, and if they want to put this new finding into their report or not. It is like the secondary interaction with radiologists. While we are doing this, actually, we also wonder, like, can we, because one of the things is like labeling is very expensive, right, in medical imaging. So can we use this, like, this eye tracking with during radiologist screening or radiology reading in the rooms? Can we use like a baseline UNet or kind of segmentation algorithm running in the background and use their just eye to segment? And even rough segmentation is fine, because we can collect so many rough segmentation and they can go into the refinement and we can get a lot of data, right? The data is still a problem in medical imaging domain. And I just want to also show here that, it's so relaxing environment that we don't really have, those laboratory constrained environments for eye tracking studies, so they can really feel comfortable and not nervous, just, do screening and continue what they want to do. They can do even multiple, the screen. This is also difficult, eye tracking, but we managed to do that. And actually we use different modalities for this, the MRI, different organs also, PET, ultrasound, and we did like rough segmentations, like where they look at it, we roughly segment it. Even you have rough segmented, they can go into the refinement for a reference standards. So we collected actually many data like this, because it was the reason was to lack of ground truth for many segmentation can be collected this way instead of doing like mouse-based, the contouring, which is really time-consuming. And we have done also another thing that, during the radiologist, often we were asked that can we do, also like quantification during this screening. For example, you find a tumor, they want to segment this, and also they want to do some measurements. So if we can do the eye tracking based gaze guided segmentation, and if we give them the volume and the dimensions of the tumor, this can be very useful for them, and they can put them into their report as well. So we did that actually. At the same time of actually what we were doing is the same algorithm came, which is the segment anything model by Meta. It was not for radiology images, but what we get that actually we use this Meta engine and we fine tune it on the header of the classifier, and then actually you see these red circles are where the radiologists are looking real time with their eye. They look at the liver, kidney, we can segment, and nowadays actually we also put the probability if there is something ongoing pathological, and we also put their volume. So if they can use it. So, and this is also useful for, some natural images as well, as you can see on the right corner. So real-time segmentation and quantification is possible with eye tracking as well. We look at there, actually the time constraint is important. Like if they can do the same thing with the mouse or eye. So it is, we see that actually the time with gaze is much smaller. So it is really, important efficiency metric for us. So this was actually also published last year in a workshop of actually gaze meets machine learning in the NeurIPS. It takes also, our code and everything is also available. So another thing is that you don't only have one screen, right? In several cases, like this case, prostate cancer screening, you have 4 images. You may have multiple screens. Screens can be divided into different arrangements. So can we use this? So again, this is a glass-based system for several years ago we have done. Now we don't use that one. We use this stereo-based. And actually this is actually Dr. Barış Türkbey from NIH, is one of the prominent people in prostate imaging. So we were actually trying to understand how he really catch all these very difficult tumors. He's a very famous person in this domain. So we did the same things for multi-screening, and we noticed that actually which images he look at most. For example, T2 images he look, and somehow he go to ADC map. He look at the diffusion imaging less, but very localized, and also the contrast images, actually, the DCE, he look at as well. So we know actually even which order actually he look at those images to collect information based on actually searching his eyes. At the same time, actually, we combine all these maps to make a prostate cancer diagnosis. So that is actually last year, I also got this grant. It is a trustable prostate cancer diagnosis where I'm putting the expert in the loop in multiple different ways. Actually, we learn a lot from him, how he actually is doing that, and then interpret them in the AI. Later, actually, we naturally, we included like speech recognition into the eye tracking system as well as a part of, because in the screening, the radiologists are also, speaking, right? So we try to include those. And nowadays, actually, again, naturally, we are trying to include them in the large language model. So integrate everything together to make a human in the loop system more realistic and can be used in the clinic. So I'm going to finish very soon. I want to show that actually in many cases in AI domain, the medical people, we borrow many ideas also from computer vision domain, but our difficulties are very unique. So you really need to put a lot of innovation and effort to make the system work. So I want to show this opposite case now. After we develop all those things, actually, there was this civil engineering work. So the problem is similar to medical imaging. So there is a human inspector doing the road and bridge inspection, but in many cases they cannot actually approach to the object. So they need to be far away, or they need to also do a lot of measurement. So we use our algorithm, and not with eye tracking, but with a mixed reality data headset to do the recognition of those crack or those the pathological condition. Let's say the image here is the whole environment, and then you are looking for pathology, and then you need to quantify. They're very similar to the radiology and the pathology, the cases. I want to show actually how it works in real time. So we actually use the similar algorithm that we have, but we just need to compress it to put it into this mixed reality set. Human just need to look at it, and then once he decides that I want to analyze this part, it automatically detects crack region. And there are also some other regions as well. And then once you actually click the button, it segments and it can tell you the quantifiable results, and it puts them into the the reports as well. Apart from crack, we can also define like the spall in different angles, and this is being tested for like breach and also roads. And actually, we also patent this, and it works real time, as you can see. So that was a civil engineering work that non-medical imaging domain, but it is the the similar working principle. Okay, to conclude my work and to discuss, like I tried to show, we have many other actually, by the way, liver and the pancreas. We try all this, the techniques, segmentation, quantification. The human in the loop actually for high risk application is quite beneficial for radiology application. For simple and very regular things, actually, probably eye tracking is not really necessary, but for challenging cases, it's really, really useful. Actually, it can improve the AI system working mechanism, and it can it can also help the radiologist to look at the certain parts that may be missed. There is a really collaborative communication there, and it is possible to personalize AI based on the whoever is actually doing the AI, the radiologist screening. So this is possible with eye tracking experiments. So future direction, actually, we are actually seeing that there should be increased integrations, like more sophisticated integration is going to be done. Currently, we have done, for example, speech integration, and we are also putting large language models nowadays. So radiology, pathology, electronic health record with an XR technology with AI, I think this is, I envision that actually many things are going to be used all together to improve, the diagnostic and prognostic applications. Adaptive systems will come. This is customizing the experience, like different users have different needs. Different radiologists have different search mechanism, and they can have the weaknesses and strength. And AI can learn and mimic this, so it can actually help you what you really need instead of just general response. So this is what I also envision, and we are working on this as well. And actually, I also think that actually multiple radiologists and clinicians can work together within one AI settings, where it can also learn from everybody, different personal perspective. And then combine also multimodal data, like, not a single modality data, but multimodal data, and multiple radiologists and also pathologists and clinicians can all use integrated into an AI hub. And AI hub actually has many different sub AI hubs that, that learns, personality, this personalization of these screeners. This is, I call it actually holistic AI. That can be also one of the future, the realities. Explainability is like, the model explainability, algorithm explainability will always be there, and, the more algorithm, will come. We are more interested in the decision mechanism, like for the explainability, like what are the reasons and causality. So this should be also part of the the overall system, which I didn't talk much about this algorithm wise, but we have some actual algorithms showing much better than GradCAM is more intuitive, similar to the human recognition. And I think real-time adaptation is really important in all our projects. Actually, we try to make it it is real-time or near real-time. So that is very important. Even the few seconds sometimes is not really it's bothering for clinicians. So we try to make this like really fit into the clinical the guideline and the routine. So currently I will show one more video, and actually I'm stopping. So we are integrating, we try to personalize AI with eye tracking, and currently we also put this large language model, GPT kind of stuff, to improve the diagnostic part. Also put this eye tracking part, like the gaze map, into the report. This is not a finished project, but I can show for a simple, this is called IC project, we call it. So everything is together, personalized AI plus GPT is there, like the LLM model, and AI is running in the back. So you can also use keyboard or speech. You just interact with the AI, and it tells you what they see in the screen. I didn't put the reporting part here. It was not, the fully, but we have really promising results. The report is also coming automatically, and there is actually extra lines where you look at it and where you don't look at it, and it also rank your summary and findings in the reporting system. So here you don't really see the eye tracking part, but there is also, the eye tracking part in this, the application. That was all. Thank you very much for listening. I hope, I think we have time, right?
Yes, let's thank you, and I'm clapping on behalf of everybody.
Thank you very much.
This was a really, really exciting presentation. In many talks, we hear one or two interesting and exciting ideas. Your talk was full of exciting ideas.
Thank you.
One thing after another. It was very, very high density of really exciting ideas. So
thank you very much.
We really liked it. So let me, I will encourage anybody who has any questions to put it in the chat. And then let me start asking about the adaptive systems. We know that in your talk, you talked about different levels of experience of different readers. And then when they look at these cases, if they are an expert, in 2 minutes, they can complete their review. And then when they are less experienced, it may take them 6 minutes. And then we saw in Elizabeth Kropinski's papers, she was showing just, medical students, they look at everywhere and then they spend a lot of time. And then when they are experts, and then they go and look at a few areas. So can you tell us a little bit about, how the AI systems will adapt to these, and then instead of the, giving your CV to the AI system, can the AI system look at your gazing pattern and then adapt itself and say, hey, for this kind of reader, I should probably help him or her in the following aspects?
Yes. So we actually, initially, our idea was to use this as a reward function, like in reinforcement learning. So we actually start doing that and, getting some promising results. Like if a person is covering all region and then finding most tumors, but at the same time, it is so many false positive. For example, a person is spend a lot of time in certain regions, like these medical students or in voice persons, then even it is not false positive, but since they spend more time, actually the system considers this like a false positive, and the reward function is negative. For expert people, they look at only some regions, and most of these lung regions are covered. The coverage region is very small. The system and they detect already like most of the tumors. Then the reward is very high, and the false positive regions are very small. Then reward is high. So the system understands this way: is the high reward. And the only caveat here was that reinforcement learning really nicely fit here. Because of this reward function interaction, but training them is very difficult. And you need a lot of data, a lot of actually time, because we don't really have like very long sequences like DeepMinds or, play this station game like hours and hours and days. Radiologists are very quick. So we notice the data is not really enough to give us stable results. Then we try to generate a artificial scan path. But that was not really, impressive idea, because we can do only data augmentation there. And then actually we change our research direction from there until we get really big data, like maybe large scale, the eye tracking study. Once, if we can do it, probably more reliable results will come. So we observe these things, and we actually now write them as just probability box, just like a prior information into our system, like the old style machine learning algorithm. Fully automated way can be done, but there is no enough data.
Yes, yes, yeah. The reinforcement learning is. I
Yes.
wish we had 10 million cases that will work really, really well. There are actually 4 questions in the chat, and then maybe quickly I will try to summarize these questions, and if you can give quick answers in the
Okay.
next 4 minutes. Seha is asking about the introducing the human bias in the systems. So what kind of precautions or actions can be taken to mitigate such bias?
Yes. So we noticed like there are some biases. We noticed in one case, the radiologist was talking on the phone and look at this one region which is not pathological. So once we notice like cases like, they go out and come back to the room, sometimes, they can be also tired.
Yeah.
Sometimes they may be also really suspect from some regions, which is artificially giving bias. So we notice actually such things as well. Currently, just there is not really direct way of defining this, but we run the algorithm second time.
Yeah,
So
I see.
this is how we try to do that. We just run the algorithm second time. One student is actually working now. Actually, is a different mechanism, like mixed of expert with eye tracking. So can we combine like multiple people's, the eye tracking, the scan path combine into one thing instead of just one personalized? We don't really know what the reasons is gonna come, what the results are gonna come, but we are working on this. We don't have direct way of removing this, but we run always second time AI.
That's good. My wife has a smart car. When I was driving one day and I was very tired, and then at some point the car said, "You are very tired. You need to rest." So maybe, maybe your gaze GNN will say something like that.
If the same person, if we can record like multiple gaze.
Yeah.
Because we try to do this now, over 20 radiologists here and other places as well. So we already did 4 times. It's very difficult to also recruit them. Their time is very valuable. If we can actually recruit them over the courses and see if they have a regular scan path, probably we can do recognition which radiologist has this scan path.
Yeah.
This can be possible. Then we can understand if it is very, very different scan path, then we can say maybe something is ongoing with the radiologist, like, you are tired or something. But there is also one thing I should also say. We initially didn't include this in our hypothesis. We forget, but over the time we understood this after talking with also Elizabeth Krupinski.
Yeah.
All the time, radiologists are also getting more experience. So their system is also slowly changing.
Yes.
Yeah, so it is a time dependent. So we cannot consider like only baseline scan path is gonna be similar. We need to also consider that this is changing over time. They are spending less time and more focused search.
I see. It is a moving target.
Yes.
Okay.
Yeah. It's difficult.
It is difficult. That's why we have smart people like yourself. Usman is asking, how do you quantitatively evaluate the language-based model when the AI is answering your questions about X-ray images?
So, there are, this large language model based, there are some metrics, algorithmic metrics. It tells you, how successful you are. We conventionally calculate them, but actually what we do is, the other metrics, like how it fits into radiology. So we have in this center, we have like more than 10 radiologists involved in this last experiment. One of them is doing the experiment, others 9, 10 of them are evaluating visually, like verbally, they evaluate. So I think this is more useful. Other one is just algorithmic evaluation.
I see. And then Yumin is asking, when you say the biological attention in the image,
it's
perception.
What is
the meaning? It's perception.
Yeah, it's a perception, and perception doesn't need to be like computer attention. We are doing actually non-medical imaging now, this experiment to really show that. So when this perception overlap with computer attention, and when it doesn't really overlap. So we have better high level vision than computers. So we did some really striking images showing to radiologists here, and computer attention show every interesting salient point, while For a striking images, they look at only one point. It's totally different. From there, we understood that they also like eye tracking is not always helpful, like for regular stuff. So it is really helpful when there is an out of distribution or case and very difficult cases. So this is what we understand actually. Perception doesn't mean computer attention, not necessarily.
Okay, and I think you addressed O's question that he was wondering, because when the radiologists look at these cases, they also change, they also get better, and then they get experience, and I think we addressed that question a little bit.
Yeah. We look at also longitudinal, how they improve. Yeah, we notice the shorter time, shorter coverage, and they are also like mostly what we noticed that the new ones actually do like the scan like in the XY plane. It is like zigzag. And more experienced one, usually they do drilling, like they are going in the Z direction very quickly, come back, and most of the time it is done.
Okay, wonderful. And then for the rest of them, if they have questions, I see your email address listed here. So I presume you are welcoming people to send you emails and answer their questions. Ulas, one more time, we want to thank you. O says that it's an amazing talk. I agree with him. And thank you. This was really an amazing talk. Thank you very much. And then for our members, and then next month we will have another talk, and I hope that will be as exciting as Ulas's talk. Thank you very much, everybody. Have a nice afternoon. Bye-bye.